We were talking about solving root equations, right? And we did this first one where it was already done for us, and this is where I think maybe people get kind of misaligned with their steps, is because initially the examples we might see in a textbook are the simpler kind, and we learn how to do that right off the bat, and then we think, okay, well, I must do that as the first step all the time in these problems, okay? The reason we squared this one yesterday initially, before doing anything else, is because the radical was already isolated for us, okay? There is a step that comes before that, but in this problem, obviously that step is non-existent, okay? And that, I think, can maybe confuse people. So I'm going to write some steps here for solving root equations. First thing you're going to do is that you're going to isolate the root term or expression, okay? Second thing you're going to do is use the inverse operation, and in this case it will be a power, an exponent, of the roots, what we call index. Okay? So when I'm talking about a root, the number out here in front, okay, that number out here in front is referred to as the index. If it's not written, it's a 2, and it basically tells you how many times we need to multiply to get the number underneath the radical, okay? If it was just 3, I'd be multiplying 3 times to get the number underneath the radical. If it was a 4, I'd multiply 4 times to get the number underneath the radical, right? Okay? The third step, so this process, if we do this process correctly, okay, you'll do that to both sides, okay? So maybe we add the phrase both sides. That will generate an equation that we have previously dealt with. So in this case, when we work with, because right now I'm going to show you is square root equations, but we could have cube root, we could have fourth root, and that kind of stuff. But the reason we're going to do mainly square root right now is because it's going to generate then quadratics or linear equations, and those are things that we've dealt with already, right? Okay. Not until I teach you fully how to solve cubics and quartics will we integrate with these types of questions that are like cubic roots or fourth roots or fifth roots or something like that. Does that make sense? Okay. But when we do have third root, fourth root, fifth root, the procedures are exactly the same. Okay. So you're going to solve that. So that's going to generate an equation that we have previously dealt with. Solve the equation from step 3. And then the fifth step will be to check all solutions for extraneous results. Okay. A key thing, and we'll talk about it when we see a specific example, but if you have 2 answers or 3 answers or 4 answers, and let's say we have 2 answers, and the first one you check is extraneous, that does not automatically make the other one your answer. It might be extraneous too, okay? And just because your first one's an answer doesn't mean automatically your next one's extraneous. You could actually have 2 answers. Does that make sense? Okay? So you need to change, and then if we have 3 and 4 and 5, depending on the type of route we're taking, you need to check them all, okay, regardless of what the first one or the second one tells you when you check it, okay? Is that okay? Number one thing on tests and quizzes that I want to get you to understand and that I'm going to require of you is you're going to be guaranteed that you're going to start off with an equation in which the radical is not isolated, okay? You'll start off with an equation like this, and I guarantee somebody will just start squaring right away, okay? In addition, your answers are going to probably have an extraneous solution. And a lot of people last year, probably at least a third of my students, they got down to the right answers, circled both, went to the next thing, never checked, okay? So those are critical. Those are key components to these types of equations. So I'm going to provide you questions that kind of judge whether you know those procedures or not. So we'll do this first example here, example number 2. There's a couple things that when we talk about isolating the root, okay, really all you have to do is isolate the root term. And what I mean by that is if you've got a multiple out in front, you have the choice of leaving it or actually getting rid of it before you use the inverse power operation, okay? So here, if we try to isolate our root term, okay, that'd be that term there, right? We need to remove the 1, so I get 2x minus 1 is equal to the opposite of root 2 minus x, okay? Some people don't like that negative out in front of the root. And this is what I was talking about. That's a multiplier. It's a negative 1, right? Now, it could be eventually in some question. I think the last question we do, it'll be like a 4 there. You can get that to the other side if you want, or you can leave it. I'll do it in both, or in this example, I'll do it both ways to show that it doesn't matter, okay? So if I go ahead and divide both sides by a negative 1, or multiply by a negative 1, I get negative 2x plus 1 on the right or left-hand side, and I get root 2 minus x on the left-hand side, right? Okay. If you left it, I'm just going to do this to the side here. If you left it alone, you would have had 2x minus 1 equals negative root 2 minus x. In each situation, you're going to now, because the root is isolated, you are going to square both sides, right? So if I square both sides, the right-hand side becomes 2 minus x. And the left-hand side, what's negative 2x squared? Oh, I thought positive 4x squared, right? Multiply those two together, and then double it, and that becomes my b term, right? Or my O and I, so I get negative 4x, and then plus 1. Is everybody okay with that? Okay. If I were to do this one in red, where I didn't move the negative over, if I square here, okay, now remember what's happening. If I have like ab squared as my law of exponents, that becomes a squared b squared, right? Well, in this case, my a is a negative 1, and my b is a root 2 minus x. Is that okay with everybody? What's negative 1 squared? 1. And what's radical 2 minus x squared? 2 minus x. And if I come over here to the left-hand side and I square that, what's 2x squared? 4x squared. Multiply those two together and double, and that gives me my b term, right? Negative 4x. And then square negative 1, what do you get? Positive 1. Is that thing right there the same as that thing? Okay. So that tells me that it doesn't matter whether I, at this juncture right here, get rid of that negative in front of my radical or not. Okay, it's totally your choice. Initially, I'm a person, because I don't like negatives, I and it's not that difficult to just move it over. I like to move it over, okay? But again, it's up to you. No. If it's a negative, so if it's a -2 and I leave it, and we'll see that in example 4 here in a little bit. It's just gonna, if I leave it, it's just gonna make my numbers bigger. But if I move it over through division, it makes my numbers smaller, and when I square them, it's more convenient mental math, but it shouldn't matter. So we'll explain that or see that in example 4. It might carry over a little bit into tomorrow because of the time that, or I guess Monday. Last class we got through that question, but I don't know if we had enough time to actually talk about that. So we'll see. But now at this stage here, okay, can we go ahead and start solving that? Is that an equation that we have some experience with? It's quadratic now, right? So it's quadratic. You're going to get everything equal to 0. So you have 4x squared. Minus 3x minus 1 is equal to 0. At this stage, guys, I'm actually going to, I want to go back real quick to this line here and compare that graphically with the yellow, just to remind ourselves of what's really going on here inside the graphical approach or graphical understanding of our solutions. If I look at that yellow thing right there, I've got it set up in GeoGebra. The yellow that I highlighted, the original equation is right here. Okay, I graphed the left-hand side, which was 2x, and I graphed the right-hand side, which was 1 minus root 2 minus x. Okay, they intersect here at point B, which is an x value of -1/4. Is it okay with everybody? So that's my solution to the overall problem. That's what I'm trying to show by hand. Okay, when we go and we square things and we get rid of that radical, what happens is that the right-hand side and the left-hand side actually transform into those two things. So the left-hand side we had 4x squared minus 4x plus 1, and the right-hand side we have -x plus 2, and that's this blue thing, right? That make sense? Okay. We get this image over here. How many times do these two things cross? Twice. If we look at their ordered pairs, they're point D and C. It's those two. So the solutions to what we have right here in this blue, there's two solutions to that. How many solutions are there to the yellow? Only one, right? Okay. So what happened here through the squaring process is that we actually generate an extra solution, all right, because of the image on the right-hand side. That's what's now happening in our mathematical approach. The one thing we need to understand is that all of the solutions for the yellow graph up there exist inside the solutions of the blue graph up there. Okay? Does that make sense? I want to make sure we understand that all the solutions that exist for the yellow are inside the solutions of the blue, not vice versa. Okay? The blue ones are not all solutions of the yellow. Okay? So that's where the extraneous thing shows up. Okay? I want to make sure that we understand, or at least can maybe somewhat justify the last step of, well, why do we sometimes get extra solutions and sometimes we don't? It's because of what happens when we square things and how we change the actual graphical approach in the background. Okay, so now we can actually factor this. So if I factor this, I'm going to use the AC method. I'm going to go 4 times -1 gives me -4. Two numbers are multiplied. You got to give me -4, but I have to give me -3. -4 and 1, right? So I'm going to rewrite this. I'm going to move it up here to give myself some room. We're going to go 4x squared. I'll rewrite as minus 4x plus 1x, then minus 1. equals 0. And remember, the AC method then should generate something that we can do factor by grouping with. So I'm going to group those two in yellow and those two in green. What do the yellow ones have in common? 4x. Brings that out and leaves me with x minus 1. What do the green ones have in common? Just 1. And that's going to leave me with 4x plus 1, x minus 1, use the 0 product property, and then this one will solve x to be negative 1/4, and this one will solve to be x equals 1. Okay? All right. Now, I need to check these. Okay? Let's say that I check 1 first. If I plug 1 and I get 2 times 1 equals 1 minus root 2 minus 1. So that's 2 equals 1 minus root 1, which is just 1, right? Does 2 equal 1 minus 1? Does 2 equal 0? No. That's an extraneous solution. That does not automatically make this an answer, though. I want to check that one. So 2 times negative 1/4, okay, is negative 1/2, right? Equals 1 minus, okay, now I'm going to have 2 minus negative 1/4. Well, that's 2 plus 1/4, right? Okay, is that 9/4? That make sense? Okay, is that 3/2? Radical 9/4, 3/2 is 1 minus 3/2, negative 1/2. So that checks out. That is a solution. Okay. Now that gets kind of messy, and especially guys in this class, whenever we can, I'm going to give you a check. I'm going to give you a technique to do this by hand. But if you think about it, let's say we're in a class and we've got 50 minutes to take a test. Am I going to have time to take every question and check every single one of them? Probably not, okay? And what I would personally do is I would go through a test and I would do the entire test, and then I would go back and like look at the ones that I'm not certain about and check those. Does that make sense? Kind of test-taking strategy that I would be comfortable with. But I'll give you a way to use your calculators to test, okay, or to check things, okay? And I let you use Desmos, I let you use GeoGebra, I let you use those things on test. I think learning those and allowing you to have them on test kind of is an incentive to try to use them and learn them in your homework. Does that make sense? So I think you're going to get to a calculus class, you're going to get to a college class, and you're going to want to know how to use these types of things because they're of a great benefit to you. And I think if I learn how to use GeoGebra, I use Desmos, I can look at this type of stuff, which is, I think, more math and a greater depth of understanding the content than just being able to run through procedures and get numbers back for answers. Okay, I want to know the understanding of why those answers are what they are, why we kick one out, why we keep the other one, that type of thing. I think that's more mathematical than just being a calculator and running through the numbers. So I'll let you use those things. Okay, so the way that we can use Desmos to kind of check ourselves is I'm going to type in the left side of an equation. I'm going to type in the right-hand side of the equation. I'm then going to identify what I want x to be. If I want x to be 1, you see how it evaluates the left-hand side and then evaluates the right-hand side, and they're unequal, so 1 must have been extraneous, right? Type in negative 1/4, and you see that they evaluate to be the same, so then that tells me that negative 1/4 was a valid solution to the equation. Does that make sense? Okay, so you can use that. The one thing that I want to make sure we understand is if this question, let's say this question right here is on a quiz or an exam or something like that, okay? And it's a handwritten test, handwritten exam, I'm going to ask you to show supporting evidence, supporting work, okay? So if student A just has the answer there to be, let's say, 2, and they circle it, and 2 is the right answer, I don't know if it is for this question or not, they're not going to get any points for that. Because what that tells me is that they either guessed, looked at what their neighbor had, or they got on Desmos, just typed in left-hand side, right-hand side, clicked on the graph, saw where they intersect, and wrote that down. Does that make sense? Which is good. I mean, that's knowledge that's how you can solve an equation, and maybe you would use that on like the ACT or something like that where they don't ask you to show work. But part of this class is being able to demonstrate that you know the procedural things that you need to go through to solve equations, because those are things that you're going to need to be able to understand the stuff that we do in calculus. You can't manage a calculus class by not knowing these intermediate algebra things and just relying solely on kind of shortcut techniques using technology to get answers. Okay, just kind of keep that in mind. Okay, so it's example 3 here. So what do I need to do right off the bat? Okay, get x to the other side. Let me show you real quick why that's important. As we're going through, the purpose of doing something to an equation and doing it to both sides is so that we get a line after that that is simpler. Okay? Now, it might have more terms. So when I say more, when I say simpler, it doesn't mean it has less terms. That a lot of times, especially with linear equation, that is the goal or the task. But we want a line that term by term is simpler. Okay? What I mean by that, let's say that I start with something like, I'll just do a real easy one here, like radical x plus 1 equals like 2x. Okay? If I ask you to solve that, but you incorrectly just start squaring right away. If I square that and square that, a lot of people are going to get 4x squared on the right-hand side. And a lot of people, what do they write on the left-hand side when they square this? If they do it wrong, what do they usually write? X plus 1. But what should I have? Because root x plus 1 actually means root x plus 1. And if I square it, it's root x plus 1 again, right? And I need to FOIL that. And that generates that, right? So here's my question. Is what I started with, that right there, line 1 and line 2, is line 2 any simpler than line 1? No. And remember, what our goal is to be able to generate a new line that represents an equation, or that creates an equation that we already have experience with. Well, that doesn't happen here. It just gave me basically a murkier root equation. Okay, one that's a little bit more difficult to solve. Okay, so that's the logic. That's the reason why we have to isolate our root term first. Okay. Now, that being said, a lot of people, if they do this right off the bat, they don't get to line 2, because if they don't know that algebra right there, they usually miss the O and I, and they just come up with this, and I think they can go through and get the answer. Okay. So we do need to isolate our variable term here. So I'm going to subtract x from both sides. So leave me negative root x minus 1 equals 3 minus x, right? Okay, what do you want to do next? Leave this up to you guys. What do you want to do next? Divide by negative 1? Okay. What are you going to do after that? Square both sides? So it leaves me with x minus 1. And the right-hand side, what's negative 3 squared? 9. X squared is x squared. And if I double those, or multiply those together and double, that gives you my middle term, right? Okay? That middle term, that thing right there is, if I went through the entire year and just kept tally of the most common mistake, and maybe I do that for the last 13 years that I've taught, in this class, the most common mistake that is seen throughout the entire year is that when we take -3 plus x squared or something like that, we forget the OI term. Okay, that's one of the biggest mistakes all year long. That's a very common question on the ACT. Okay, they'll say, what is an equivalent format of -3 plus x, and they will write, option A right off the bat. Option A will be 9 plus x squared, and people see that right away and they circle that or color that one in. They go to the next question. Or option B would have been 9 minus 6x plus x squared, right? Okay, so it's known that is a common error. So people that write standardized tests play to that. Okay, so make sure you're aware of that. So now this is quadratic, right? So it's quadratic, so we can solve that. So I can go ahead and I'm going to rewrite this as x squared minus 7x minus plus 10 equals 0. Just moving everything to one side. So I go to x minus 5 and x minus 2. So then x is going to be 5 or x is going to be 2, right? Now if I plug that stuff in, if I plug in x to be 5, I get 5 minus root 4. Does that equal 3? Does 5 minus 2 equal 3? Yep, so 5 is the solution. Does that mean 2 is automatically extraneous? No. Plug 2 in, I get 2 minus root 1. Does that equal 3? Does 2 minus 1 equal 3? No. So that is, it does end up being extraneous, but we have to check. And this is the reason we have to check. Let me see if I can create a situation here with just this first question. Let's say that I had, get rid of that. We'll get rid of that. All right, so this was that first example we went through. If this 2x would have been something instead of 2x, let's say that it was 1/2 x. How many times does that intersect? Twice, right? So when I go through the squaring process, okay, when I go through the squaring process, there's going to be 2 intersections in that second graph, right? Does that make sense? And those both end up actually being true solutions to this because this had 2 solutions. All right. So just the nature of however that first set of graphs set themselves up and intersect does not allow me to automatically, when I have one solution, make the other one extraneous. They could both be true solutions. Yes? Up here when I plug back in, because the square root is already there. Like if I had like x squared is equal to 4, that is the question. What number can I multiply by itself 2 times to get 4, right? So that's why I get x to be plus or minus 2. There's 2 solutions to that question. If I say like radical x equals 2, because this is positive, right? Out in front, I don't have any marker in there. There is one and only one number that when I plug in here, like 4, that is going to give me 2. Because I plug -4 in, or I make it a negative out here. So if I went negative square root of x like that, what is the number that does that? Okay. I'd square both sides. Okay, is there a number that I can plug in here that's going to give me that? No, there won't be. If I look at negative square root of x, what that does, so square root of x looks like that on the graph. Negative square root of x looks like that. 2 is that line. They never touch, right? So there's no solution to that. But the idea is because of this question right there is why we bring in 2 answers at that juncture. You see how that's different than what I'm starting with here? I can see, and the more we do, I think the eventually you'll overcome that want to do that. And I understand that confusion that people have that question every year. I'll spend some time see if I can articulate that answer a little bit better, but that's the reason why. What's different about this example than the ones we've done so far? 2 radicals. So here's my question. Can I isolate both of them simultaneously? No, can't. Okay. I could if that 2 wasn't there, right? That 2 plus or whatever. If that was gone, then I just square right away and be good to go. If I have 2 radicals that are the same, then that means their radicands have to be the same. It's like if I had 1/2 is equal to x over 2. Well, that's a 1-to-1 correspondence. It means x has to be the same as my numerator on the other side, right? So here, if I had 2 radicals that were identical, okay, so let's say, let me just kind of prove this to you real quick. If we had just that, okay, well, that is saying essentially the same thing, that if those are going to be equal, then those have to be equal. Does that make sense? Okay, and that's what we call a 1-to-1 correspondence. But if I've got this here and I can't get that 2 away, this is the approach that you go through. You're going to isolate one of your radical terms. Doesn't matter which one. One of them is already done for us, right? Okay. But if there was like a plus something on the left-hand side, we would have to do some work to get one of the sides to be all radical to be all by itself. You're going to square it right off the bat. Okay. Once you've isolated a radical, now start squaring. I'll square the left-hand side, square the right-hand. Squaring the left-hand side is pretty easy, right? Gives me 3x plus 1. Squaring the right-hand side, this is where you've got to be careful again. I square 2, what do I get? 4. Now, remember what this means. It means 2 plus root x plus 1 times 2 plus root x plus 1, right? So I got a FOIL. So I'm going to take outside times outside, so it gives me plus 2 root x plus 1s, right? Then inside times inside gives me another 2 root x plus 1s. And then last times last will be squaring a radical, which just gives me the radicand, right? Gives me the x plus 1. Now there's a lot of like terms here, so I'm going to go through and take care of those. I got that 4 and that 1 gives me 5. I'm going to have this plus x, and now I've got these 2 things as like terms. They have the same radical, so we can add the coefficients or the multipliers, and I get that. Is that all right with everybody? Now, here's my question. Is that simpler? Maybe not in the number of terms. I don't want to count the terms and do that kind of thing, but is the structure simpler now than what I started with? Because what I started with had multiple radicals, right? This structure has 1 less. And that's the overall goal. Can I get to something that is less complex than what we started with? But it's not completed yet, okay? We still have a radical. So all we do is we play that game again. We isolate the current radical, go through the inverse operation, see what we come up with. So I'm going to subtract the 5 over, subtract the x over. So that gives me 2x minus 4 is equal to 4 times root x plus 1. And this is what you were asking about, Anthony, earlier, is if there's a number out in front of the radical, do I need to get rid of it? And here's the answer to that. No, you can leave it alone. And I don't think we'll have time today to show the multiple versions of this. I'm going to leave it alone, okay? The safest thing to do, I think, would actually be to see if there's a GCF and everything up there. Can I factor a 2 out of everything? Divide a 2 out of everything? Yeah, so I could write the left-hand side as x minus 2, the right-hand side as 2 times root x plus 1, right? And the reason I would do that is I'd rather square 2 than squaring 4. Does that make sense? Now, 2 and 4 is not a big deal, but later on, if these numbers were much bigger, maybe it is a big deal. I would not want to divide everything by 4, because when I divide everything by 4, that term becomes 1/2, right? Does anybody really want to square 1/2? Probably not, okay? So that's kind of the foreshadowing that I do mathematically to think about, okay, what is going to be easier for me, okay? I think dividing everything by 2 would be nice, but even though that's nice, leaving this alone really isn't all that bad. So I'm just going to square right away, okay? When I square the left-hand side, it gives me 4x squared minus 16x plus 16. The right-hand side gives me 16 times x plus 1, right? Does that make sense? Because this is kind of like an a times b squared concept. A being your 4, so you square that. B being your root x plus 1, so you square that, right? That's what I get. So this gives me, I'm just going to go ahead and rewrite this as 4x squared minus 16x plus 16 equals 16x plus 16. What happens with that 16 and that 16? They cancel, so it leaves me 4x squared. I'm going to move this 16x over at the same time, so it gives me 32x equals 0, right? Okay. What do they have in common? 4x. So let's take that 4x out. And we're left with x minus 8 equals 0. Can I divide both sides by 4? Or do this first. And I could divide both sides by 4 if I wanted to before here. But when I do that, is x 0? Is x 8. Does that make sense? Okay. Now, we do have a little bit of time here, so let me, at this stage, what if we did divide everything by 4? Oh, let's just divide everything by 2. So give me x minus 2 equals 2 times root x plus 1. If I square all that stuff, I get x squared minus 4x plus 4. On the right-hand side, I'm going to get 4 times x plus 1. So we get x squared minus 4x plus 4 equals 4x plus 4. That 4 and that 4 are going to cancel out, right? And we get x squared minus 8x equals 0. Okay. Does that still factor to x and x minus 8 equals 0? Does x equal 0 and x equal 8 there? Does that make sense? So at the juncture where I could have gotten rid of that 4 somehow, maybe divide it by 2 or divide it completely by 4, all that's going to do is make, at that stage here, those two numbers or these two numbers, or if I would have divided by 4 completely, it would have gone down even further from 1 and 8 to something else. Okay, it's just going to make those numbers smaller. Does that make sense? If I do that division of that multiplier. Now, when I go back and check, if I plug 0 in to the original problem, okay, I get 1 here, right? Does that equal 2 plus? I don't even care what this is. Is 1 ever going to equal 2 plus something? No, so 0 does not work. 0 is extraneous. If I try 8, that's 24 plus 1, so it gives me root 25, right? Does that equal 2 plus or minus? That's 9 there, right? With 8. Does root 25 equal 2 plus 3? Yes, so 8 would be my only solution in this case. But does that make sense on why I don't necessarily need to get rid of a multiplier out in front? Okay. It is safe if you're a person that struggles with squaring a product, then maybe safe in terms of safety, yes, do get that over to the other side. But if we understand our algebra, it doesn't matter. Okay. And those are the through this class. That's what I'm interested in, guys. I know you've seen some of this stuff before, but you've been taught the procedural stuff, right? I want to get into things and say, okay, why can't I do this? Why can't I do it a different way? Give myself options. Does that make sense? And see attacking problems in different formats, how that can maybe benefit me.